Hello and welcome back. In this video, we're going to be taking a look at how to break down a given scenario and not only sketch what that scenario might look like, but also identify the concepts from that scenario. Let's begin. In the first scenario, we have a mass hanging on a spring in equilibrium. Well, the sketch is pretty simple. Just draw a spring, a mass hanging on the end of it. Now, one thing to note, I'm going to color code how I write certain things. In black, I'm going to be color coding the things that we absolutely need to know. In blue, I'm going to be color coding the things we need to be able to derive. Okay, so for instance, you would need to know that if you have a mass hanging on a spring, you would need to know what forces are acting on that mass. Weight equals mg, and spring force equals kx. The concept is Newton's first law. Remember, N1L is an abbreviation for Newton's first law. But it's also referred to as static equilibrium. And the formulas that go with that, well, the main formula that should go with it is that the net force acting on the system is zero, or simply put, forces up equal forces down. Now, this is the main equation you need to know. You need to be able to derive what the actual equation is from the forces you identified earlier, meaning these. So the forces up would be kx, and the forces down would be mg. Kx equals mg would be the equation that we use for this particular scenario. In the second one, we have a mass hanging on a spring, but it's acting as an oscillator. So I'm going to draw a dashed line to represent the equilibrium position. I'm going to draw another dashed line to represent one amplitude. I'm going to draw another dashed line to represent the other amplitude. And this mass oscillates up and down between these two, right? It might look like this. Well, the concept involved here would be simple harmonic motion, which we'll abbreviate SHM, of a mass spring oscillator. Now, what formulas do we need to know that match this particular concept? Well, one, we need to know that the period of any oscillator is 2 pi over the angular frequency omega. Specifically, we need to know that the period of a mass spring oscillator is 2 pi times the square root of the mass divided by k, the spring constant. Now, from this information, if we take 2 pi divided by 2 pi square root m over k, we get the idea that omega is equal to the square root of k over m. And we can derive that. We can figure that out. Okay. Again, if you see up here, 2 pi over 2 pi times the square root of m over k for we're switching those two, so that should be omega. There we go. Okay, the 2 pi's cancel, leaving you with a 1, and if we take 1 over the square root of m over k, that would just simply be the square root of k over m. In the next scenario, we have a mass that is compressing, right? It's going to be compressing it's compressed against a spring, and then it's released from rest. Initial velocity is 0. And when it's released from rest, we have a situation where two energies can be seen and present. Conservation of energy, COE, abbreviated, would be the concept that we can link to this particular scenario. And conservation of energy is noticed and identified when you can observe two potential changes in energy. So for instance, earlier on, when we compress the spring, we have spring energy stored up in that compressed spring because the spring wants to do work to restore itself back to equilibrium. Once the mass is flying, it now has kinetic energy. Since there are two changes in energy, we can use the law of conservation of energy to analyze the problem. Now, the main equation you have to know is total energy equals kinetic energy plus potential energy, and that total energy initial equals total energy final. That you have to know. What you need to know how to derive in this particular scenario is that the initial energy in this case would be spring potential energy, which is 1/2 kx squared. And the final energy would be kinetic energy, in this instance, 1/2 mv squared. Well, the next scenario we have is really just the reverse of the third scenario. So we have a mass that's sliding, but it slides into a spring and then ends up compressing it. So let's draw the picture in reverse order. There's the spring. There's the, there's the mass. It has initial velocity. Okay, and then it's eventually going to come and strike the spring and compress it. So initially, we have kinetic energy because we're moving. And when we have a fully compressed spring, we will have stored up spring energy. So since we are observing two changes in energy, conservation of energy is again the concept we would use. So we need to know that total energy is kinetic plus potential. We need to know that total energy initial equals total energy final. And we must be able to derive in this instance the initial energy, 1/2 mv squared, equals the final energy in this instance, 1/2 kx squared for spring potential energy. In the next scenario, we have a pendulum oscillating and we're trying to find g, the acceleration due to gravity. So we're just going to draw a pendulum arcing through the bottom of its swing from one endpoint to another. we go. Okay, there we go. So we have a pendulum oscillating back and forth, and the goal is we're trying to find G with this. That's usually the most common goal in this particular scenario. Now, the concept in this one is simple harmonic motion again, but it's simple harmonic motion of what is called a simple pendulum. A simple pendulum is defined as a pendulum that has essentially a massless string attached to a bob at the end of the string, and the bob is the only thing that has mass. From this, we need to know again that the period is equal to 2 pi over omega. We need to know specifically the period of an oscillating pendulum is 2 pi times the square root of the length of the pendulum divided by G. Remember, that's the goal, find G, right? And then from this, you should be able to derive the fact that if we switch those two, omega equals 2 pi over t, which is 2 pi over t, and t is 2 pi square root of L over G, cancels, and 1 divided by the square root of L over G means omega for a simple pendulum would be the square root of G over L. All right, in the next scenario, we have a pendulum, but this time we're trying to find something different with the pendulum. We're trying to find the speed at the bottom of the swing. So we take our pendulum, we raise it to some highest point, and we let it swing down to the lowest point, just like this. Okay, and we want to find the speed at the bottom of the swing. Well, the speed is associated with kinetic energy. This represents the height, and the height is associated with gravitational potential energy. This is another instance in where we have two changes in energy. The gravitational potential energy decreases, the kinetic energy increases. We can therefore use conservation of energy to find the speed at the bottom of the swing. So we need to know kinetic energy plus potential energy is total energy. We need to know that total initial energy equals total final energy, and we must be able to derive in this instance a couple things. One, make this a little smaller. The first thing we should be able to derive is the initial energy is gravitational potential energy, so mgh to start with. And afterwards, at the bottom of the swing, it's been fully converted into kinetic energy, 1/2 mv squared. But here's the next thing we must be able to show for a simple pendulum. Let me log in on the picture here. This is what you must be able to derive and figure out. In order to figure out the height, you need a couple things. First, you need the entire length of the pendulum string, which is the entire length of the string here. Okay, you also need this particular segment of the string, which is, if this is the angle from the vertical, this side segment here represents the adjacent side to that angle, which would be the length L times the cosine of that angle. Therefore, this plus this equals the entire length L. So L equals H plus L cosine theta. Therefore, H is equal to L minus, in other words, solve for H, it's L minus L cosine theta. But of course, you could factor out an L in the process, and this becomes mg L times the quantity of 1 minus cosine theta, right? If I factor out this, factor out the L, what's left over? 1 minus cosine theta. equals 1/2 mv squared. Okay, so this is what you must know. This is what you need to be able to figure out within the scope of the problem. Now, in the next scenario, you have a pendulum, but this time you're trying to find the tension force at the bottom of the swing. So I'm going to start with that pendulum again. This time I'm going to focus my attention only on the bottom of the swing. I don't need to know anywhere else. So there's the pendulum swing. Okay. But this time what I need, and I'm going to make my picture just a bit smaller. There we go. I need, since we're trying to find tension, I need the forces acting on. So I must know how to figure out my forces. I have weight pointing downward, but it's not just downward, ladies and gentlemen. It's, if this is my circular curvature, it's pointing out of the circle. And I must, of course, be able to see that tension is not just pointing up, but it's pointing into the circle. Okay, this is an example of not only Newton's second law, but centripetal force. And centripetal forces are forces that cause curvature. So when we derived Newton's second law, we broke down net force equals ma into a causing force minus opposing force equals ma. Causing force causes acceleration, points in the direction of acceleration. Opposing forces oppose acceleration, point against acceleration. Well, causing forces point into the middle of the circle. Opposing forces point away from the middle of the circle. In other words, out of the circle. Okay, from this we need to know centripetal acceleration is equal to v squared over r, which means the net centripetal force, which is ma, is really mv squared over r. But you should be able to rewrite this as causing force minus opposing force equals mv squared over r. But what is that really? Forces into the circle minus forces out of the circle are equal to mv squared over r. Okay, now you should be able to look at this and derive from the actual problem. In this problem, we had tension pointing into the circle minus weight pointing out of the circle is equal to mv squared over r. All right, in the next scenario, we have a position versus time function, but it's a cyclic function. So cyclic refers to sinusoidal. Now, a sinusoidal function would either be a sine function, a sine graph, or a cosine function. It's going to be one of the two. So if we see a mathematical function with sine or cosine in it, that's going to be a sinusoidal function. Okay, now in this one, there's no picture necessarily. You would be given instead a sinusoidal function position as a function of time. So you'd be given either a sine or a cosine function. The concept for this would be a simple harmonic motion wave function. And you would either be given some function as a number, which is the amplitude of the simple harmonic motion oscillator, times the cosine of omega t, or if the clock starts a little bit later as the object is passing through equilibrium, then it might be a times the sine of omega t. So it could be a sine or a cosine function. Doesn't, I've seen both provided. Now, in addition to this, you must also know that if t is equal to omega 2 pi over omega, by swapping those two, we need to know that omega is equal to 2 pi over t. And in the last scenario on the first page here, we have a graph of a horizontal displacement versus time where the amplitude is cyclical. So amplitude cyclical, we're talking about a wave function. So the concept is the same. But we'd be given a sinusoidal function. Most often or not, the function is going to be a cosine function. So I'm going to write that down. However, every once in a while, you are given the position function as a sine function. Again, you need to know that omega is equal to 2 pi divided by the period. So now, if the graph is a vertical displacement versus time where the object is released from the equilibrium, so I'm going to make that little designation, object released from the equilibrium position. Okay, now that would not be true for a pendulum, because if you have a pendulum at the equilibrium position and you release it, it's just going to hang there. It has no reason to want to move. But if you have a mass spring oscillator and here's the equilibrium position and you release the mass, it's going to drop to the lower amplitude and then rise to the higher amplitude. So this would be a situation where you could be, and I'll leave the sketch on here, you could be given a sketch, or you could be given an image, but you could also be given a position as a function of time, but this time it would be a sine graph because you're starting from equilibrium. This is again a simple harmonic motion wave function, but this time the function would be a sine omega t instead of a cosine omega t, where omega is still 2 pi over the period. Okay, so now let's say we're given a graph of potential energy versus position. Usually the graph looks something like this, where this is the equilibrium position here. This is one amplitude, which I'm going to designate with a dashed line, and this is the other amplitude, which I'll put negative A, and this is the other line that I'll represent that with. And somewhere up here we have energy in joules versus distance in meters. And somewhere up here, you have the total energy E. Well, a graph of potential energy versus position would look like this, where you have maximum potential energy at the amplitudes and zero potential energy at the equilibrium. Okay. But you would be asked to figure out the kinetic energy graph. Accordingly, would have no kinetic energy at the amplitude and maximum kinetic energy at equilibrium, no kinetic energy again at the other amplitude. So you'd be asked to derive and figure this out. How would we do that? Using conservation of energy, which we need to know is kinetic energy plus potential energy. Okay, so it's not only conservation of energy, we're also looking at simple harmonic motion because we're oscillating between two endpoints. But conservation of energy would help you solve the problem. Now, a graph of total energy versus position is very much the same thing. We're given energy on the vertical axis. We're given energy in joules. We're given distance in meters. Still have this amplitude here. Still have this amplitude here. Still have equilibrium in the middle. But this time, your total energy is just going to be constant all the way across. Okay, again, this is a conservation of energy and simple harmonic motion scenario. And the only equation we really need to know with that is that kinetic energy is the sum of, the total energy rather is the sum of kinetic energy and potential energy. Okay, now in the next scenario, what if we are given and shown a mass revolving around something else and you're given a radius and the speed of that mass? So you've got your object and something is revolving around. And we're given a certain speed and a certain radius. Well, if that's true, then something has to be causing this curvature that we're noticing here. And that something would be a centripetal force. Okay, but it could be other things as well. It could be UCM, which stands for uniform circular motion. Could also be angular momentum. Of a particle or point. When I say particle, I'm referring to any point mass. Okay, so equation-wise, we're looking at net force equals ma, which in this case is mv squared over r. You should also need, with uniform circular motion, the total distance divided by the total time, 2 pi r over the period. You should be able to derive the fact that net force is force into the circle minus force out of the circle equals mv squared over r. For angular momentum, we should be able to note that for a particle, it's mvr perpendicular. Okay, now since the radius is perpendicular to the motion, okay, then we don't need any vector component for that radius. Now in the next scenario, we have a mass connected over a string over a massless pulley, which is in static equilibrium. So static equilibrium, the word equilibrium, we all need to know, means we're not accelerating. But static means we're not moving. Okay, so they're not moving. We're not accelerating because we're not moving. And this scenario that we're describing here, multiple masses connected over a pulley, can really be described in a couple ways. You could have one mass on a horizontal surface connected like this to another mass. You could also have a pulley, a mass, and another mass. Okay, but being in static equilibrium means that the system of masses is not in motion. That concept would be a Newton's first law concept, which again is a static equilibrium concept. And when we have a static equilibrium concept, it's very simple. Forces up equal forces down, and all forces going to the left would equal all forces going to the right. So if I were to look at this here and come up with the forces acting on this, we would have M1G, we would have M2G, we would have tension, and we would have tension. Here we would have M2G, tension, that same tension, static friction. Static friction in the tabletop preventing the block 1 from moving the system. The weight, right, and the normal force. What would we need to know from this? From this picture, you should be able to derive the fact that, let's say in the horizontal scenario, that the total friction that is preventing the motion is balanced with the tension. Forces left equal forces right. But since that same tension also balances the weight, we can connect this and say the weight pulling on mass 2 is really equal and opposite to the friction that's holding the whole system from motion. Okay, similarly, tension would balance and equal weight 1. That same tension would also balance and equal weight 2. Therefore, weight 1 equals weight 2. Okay, it's about balancing our forces. Now, what if we have a scenario where we are, in this case, we're passing masses connected over a pulley, but this time we're accelerating? Well, now the situation's a little different. Still have the same possible pictures. And by the way, there are more pictures than this. You could have, I've seen scenarios where you have a mass on an inclined plane, pulley at the top, with a mass hanging over the edge. I've seen various scenarios where you have masses connected by a pulley. But these are the two most common ones that you end up visualizing and seeing in problems. So I'm going to work with those. Okay, so for instance, maybe mass 2 is accelerating downward, which means mass 1 would accelerate upward at the same rate. If mass 2 is accelerating downward, that means mass 1 would be accelerating to the right at the exact same rate. This is an example of Newton's second law, but specifically, it's Newton's second law with multiple mass. Now, what does that mean? How do we apply that? Well, Newton's second law is applied as net force equals ma. But this time you have more than one mass. So you could actually apply this as net force equals total mass times acceleration, which in this case would be whatever the causing force is minus whatever the opposing force is equals all of the mass in the problem added together times A. Now, what if we have masses connected by a light string accelerating together? There's mass 1 connected to mass 2, and mass 2 is being forced to the right, which means the system is accelerating to the right. Whether there's friction in the surface or not is, sometimes there's friction, sometimes there's not. But this is also a Newton's second law problem with multiple mass. And it's also a situation where we have net force equals the total mass times acceleration. Now, by doing it this way, you're able to find the acceleration of the entire system. If you wanted to find the tension in the string, you would simply focus on only the forces acting on one mass. Okay, so if I wanted to find the tension in this string here, I might only focus on the forces acting on that mass, which would be, horizontally speaking, tension and friction. Now, let's say you have a scenario where you have masses connected by a string over a pulley, but this time the pulley has mass. And if it has mass, it has rotational inertia. Okay, a massless pulley is referred to as an ideal pulley. An ideal pulley is one that has no mass and essentially no friction. So if we take the exact same scenarios that we had before, we would have a mass accelerating, or two masses accelerating, but this time you'd be given the radius of the pulley and the mass of the pulley, because now the mass of the pulley matters. Okay, you'd be given that information. So it's still Newton's second law with multiple masses. But this time we don't really apply the Newton's second law with multiple masses. We just apply Newton's second law on each mass separately. Right? But you're going to also apply rotational Newton's second law on the pulley. So what do I mean by this? Well, net force equals ma on each mass, which means you need to be able to figure out what the causing force minus the opposing force equals ma for each mass. But you also need, for the pulley, net torque equals I alpha. Okay, so in addition to that, you need to know the torque equation is a perpendicular force times distance, and you need to be able to substitute for alpha by knowing that the tangential acceleration is equal to r times alpha. Similarly, you should be able to break down a net torque into a causing torque minus opposing torque equals I alpha. Causing torque would cause the object to rotate in one particular direction. The opposing torque, of course, resists that rotation. In the next scenario, we have a mass, a spinning mass, and we're given the mass, the radius, and the rate of rotation. M, R, and omega. That could be as simple as something just rotating on an axis. That's what the lines represent there. That could be anything from, if we're given the angular velocity, that's used in rotational kinetic energy. It's also used in angular momentum. Which corresponds to 1/2 kx, 1/2 I omega squared, and L equals I omega. Okay, now something else that usually has to be applied along with these is V equals R omega. It's the translation between tangential and angular velocity. Now in the next one has a point P some distance away from an object. Okay, now this is typically R, the distance away from that object. Now, the way we can describe this is if we were to look at the perpendicular component of R, which would be R sine theta, if we make this theta. Okay, then this is an example of an angular momentum problem as well. But this is an angular momentum of a particle or a point mass. Now, what you need to know is you need to know that the formula for the angular momentum of a particle is mv r perpendicular. Now, if that object is right over a particular point of reference, then it's just going to be, that ends up being r, right? R is just this short little line right here. But if it's some distance away, then we take the perpendicular. So in other words, we're always taking the perpendicular distance to the point at which we're moving about. And notice that this object is moving linearly. It's not even revolving around this point. Okay, but we're talking about the perpendicular component to that point. Okay, will always be used. So we could derive that as mvr sine theta. Now in the next scenario, we have a mass spinning about an axis of rotation, and we're given a rate of rotation. So it's a same situation as we had in the first scenario. Same concepts that we have in the first scenario. In other words, the third scenario is really just, and you find this quite often, how given slightly different information, yet it's the same idea. So here we're talking about a spinning mass, and we're given mass, radius, and a rate of rotation. This time, where it's a mass spinning about an axis of rotation, and we're given the radius and the rate of rotation. We may or may not be given the mass. Okay. Rotational kinetic energy, 1/2 I omega squared. Angular momentum, L equals I omega, and again, V equals R omega. And you have to be able to use this to solve for omega, which would be V over R. Okay, now we get into some more applications involving collision. So let's say we have a mass collides with a rotating rod. So let's draw the rotating rod. I'm going to draw a before and after sketch. anytime there's a collision, always draw a before and after sketch. Okay. So before, you've got your rotating, you get your rod that can rotate about the end right here, and it's not moving. So the initial omega, right, is 0. It's not moving. You have a mass that's moving and about to collide. Now, it doesn't say in the scenario where it's going to collide. Just for simplicity, I'm going to say it's going to collide at the end. But really, this problem is the same concept no matter where it strikes the rod. Now, it says that causing the rod to rotate and the mass to stop. So after collision, the mass stops. And the rod rotates upward with angular velocity omega. This is a concept known as conservation of angular momentum, COAM. Again, that's abbreviated conservation of angular momentum. Okay, and the way conservation of angular momentum works, it works in all collisions, but it works under the idea that no net torque is acting on the system to cause some sort of change in the rotation. No net torque caused it. So since there's no net torque acting on the system, angular momentum is conserved, which means the angular momentum before equals the angular momentum after. Okay, and so here's what we need to do. Go back to this right here, and we need to reason out. This has MVR of angular momentum before. This has angular momentum of I omega afterwards. Okay, and I'm talking specifically about this because this object stops, where this object was at rest beforehand too. So now putting it all together, we have to be able to come up with the initial angular momentum would be MVR equals the final angular momentum, I omega. Okay, and yes, you might need V equals R omega if you're trying to convert that from, let's say, omega to V, or, you know, what have you. In the next scenario, we have a rotating rod. This time the rotating rod is going to strike the mass. The rod will stop moving and the mass continues. So think of a golf club. Okay, so we have a rotating rod. Rotating about that point there, it's going to strike a mass right at that point right there. So this object here has initial velocity omega. It's swinging downwards. Okay, afterwards, the rod stops upon hitting the object, and the object, the mass, flies forward with velocity. Okay, this is the exact same concept as the previous one, conservation of angular momentum, which means angular momentum before collision equals angular momentum after collision. Same as before. But here's how we need to apply it a little differently. Initially, all we have is the rotating rod, which would be I omega. Afterwards, all we have is the linearly moving mass, which would be MVR. Which means we need to be able to come up with I omega for the initial angular momentum equals MVR for the final angular momentum. Okay, and again, yes, V equals R omega can be helpful when we have two different types of velocity units there. Okay, what if we have a rotating mass changing its radius? So picture a person on a stool, or even a figure skater for that matter. So we have a person here. I'm going to draw a before and after here too. So before, let's say we have a person with arms stretched out like that. And they're rotating at a particular rate. Okay, and then afterwards, they bring their arms in central to their body. What ends up happening? The angular velocity increases with this. Again, this is a conservation of angular momentum problem because the angular velocity increased, but not due to a net torque. There was no external torque pushing on this person to get them to spin faster. In this instance, we have a rigid object rotating about the center. We have another rigid object rotating about the center. This person is representative of a rigid object. In other words, we should be able to come up with I omega initially equals I omega finally. And it's I initial, omega initial, I final, omega final. So what's happened is the rotational inertia has gotten smaller, therefore the angular velocity has to balance that and gets accordingly bigger. What if we have a force time graph? Let's say we were given something like this. Well, a force time graph has a concept of impulse momentum theory attached to it. Okay, but do keep in mind that an impulse is also a change in momentum. Okay, and what we can get out of this is that J, which is the impulse, that's the variable for the impulse, is equal to the area under a force time graph. Okay, so all of this, right, would be the impulse, okay, or the force applied over a time interval. And lastly, on this page, we have a planet orbiting a star. So here's a star, here's a planet, and it's orbiting at two different radii. So picture something that's elliptical. Let's say this is point A, let's say this is point B on the far end of the orbit. That would make this radius A, that would make this radius B. Velocity A is much bigger than velocity B because the distance is shorter. Again, this is a conservation of angular momentum problem. The velocities are clearly changing, okay, but not due to an external torque. There's no net torque acting on the system. When that happens, the angular momentum before equals the angular momentum after. Now, we should be able to come up with the fact that this right here would be MVR at point A, and this should be MVR at point B. Which means the initial angular momentum would be MVARA, assuming that's the initial point, equals MVBRB. And yes, you can cancel out the mass. The mass of the planet stays constant, and so we end up with V times R equals V times R. In this next scenario, we have a situation where you could be given any force vector. And this isn't necessarily a specific physics concept, as it is more really a general concept that is found anywhere. Any vector is a quantity that has a magnitude and direction. And if that direction happens to be pointing at an angle other than horizontal or vertical, then we need to apply what are called vector components. And a vector component is simply any vector, and for the use of this particular example, I'm just going to call it some force vector, F. And let's say it's applied at some angle above the horizontal. The adjacent side of that angle is force times the cosine of the angle. And the opposite side of that angle would be the vector magnitude times the sine of that angle. And the generalized concept would just simply be that of vector components. And in a generalized way of stating this, vector components are the adjacent component would be whatever the vector is times the cosine of the angle. The opposite component is whatever the vector magnitude is times the sine of the angle. Now, what if we're given a situation where we have a mass that's rising or falling? Well, this could be a couple different concepts. Image-wise, right, we're looking at an object that's simply rising or falling. Well, that could be a free fall acceleration example if we're talking about kinematics and kinematic variables such as distance, time, acceleration, and velocity, or it could be conservation of energy, simply because a rising or falling object has a change in kinetic energy and a change in gravitational potential energy. Remember, in order to be a conservation of energy applied concept, there must be two changes in energy. Okay, and that's definitely true in this example. So if we're looking at free fall as the concept, right, then the following equations would be Vy equals V naught in the y direction minus g times t, or y equals y naught plus V naught y times t minus 1/2 g t squared, or Vy squared equals V naught y squared minus 2g times y. If we're talking about conservation of energy being the concept, well, then it's simple as energy initial equals energy final, and relating your individual energies, whether they be kinetic energy and potential energy. Well, what if we have a moving mass and we're given, now the moving mass, let's say the moving mass is at a constant speed, right? And we're given distance and time. Well, you're given kinematic variables. So if you're moving a mass at a constant velocity, well, that would either be a constant speed or velocity concept, or it could be an average speed. Or an average velocity concept. Now, if it's an average or a constant speed, then it's as simple as speed equals distance over time. Okay, if we're talking about velocity, then we're talking about displacement over time. What if our scenario has a mass moving at a constant speed given a force acting on it? So we have, and I should say really forces, because if it's one net force, it would not be moving at a constant speed, it would be accelerating. So I'll say forces have to be acting on it. So let's just say, for example, we have an applied force on an object and an equal amount of friction resisting that object to allow it to move at a constant velocity. Yes, there'd be weight, and yes, there'd be normal force, but they don't contribute to the motion. The concept would be Newton's first law, because constant velocity is a balanced force situation. We're not accelerating. This would be known as translational equilibrium. And that would be simply forces left equal forces right. Okay, now what if we have a mass changing speed horizontally? So now we're talking about if you're changing speed, you're accelerating, right? But we're given position, velocity, and time. We're given kinematic variables. So if we're talking about a mass that's accelerating given kinematic variables, that is a constant acceleration idea. Okay, constant horizontal acceleration. And the there's 4 formulas that go along with constant horizontal acceleration. We have v equals v naught plus a times t, very similar to this equation here. We have x equals x naught plus v naught t plus 1/2 a t squared, very similar to the second equation here. We have v squared equals v naught squared plus 2ax, very similar to that third equation right there. But lastly, you also have that displacement is the average velocity times time. So we just change average velocity into final velocity plus initial velocity over 2 times t. That would be the 4th constant acceleration equation. All right, now what if we have a situation where we have a mass changing vertically? Well, if we have a mass changing speed vertically, that means we have a mass that's essentially being dropped or thrown upwards. That is exactly the same thing that we saw a few scenarios earlier. That would be a free fall acceleration problem if you're given kinematic variables, or a conservation of energy problem if you're involving only height and speed. And therefore, it would be the exact same concepts and formulas as we presented in the scenario above. Now, what if we have a mass that's moving horizontally but ends up flying through the air? What would that look like? So we have a mass that's moving, but ends up flying through the air. Well, that would be a horizontally launched projectile. And there's 2 equations that become very useful for a horizontal launch projectile. One, if you take this equation here, y equals y naught plus v naught yt minus 1/2 gt squared. Okay, and you chop down the idea that at the floor, the final position is 0, The initial velocity in the y direction is 0 because you're launching it horizontally, not vertically. You're left with 0 equals y naught minus 1/2 gt squared. So we can really write this as y naught, the height of the cliff or tabletop or whatever the horizontal surface is, equals 1/2 gt squared. Sometimes I've seen it just written as h, the height, equals 1/2 gt squared. That would be fine as well. And you also have x equals v naught x times t. Now we get this one from the idea that in the x direction, the horizontal direction, we take our horizontal equation for acceleration, and we recall that in the x direction, horizontally speaking, the projectile does not accelerate. It only accelerates in the y direction. So there is no acceleration in the x direction, and you can see what results. X equals v naught xt. And in this next scenario, let's say we have two masses that run into each other head on but don't stick together. Okay, now anytime we have a collision, just like we did with angular momentum, we're going to draw before and after scenarios. So we have a before situation and an after. Okay. Now before, we have a situation where we have one mass, I'll call it mass 1, and we have mass 2, and they're going to collide. Now they could collide in a variety of ways. 1 could smash into 2, 2 could smash into 1, or they could simply be going in opposite directions and smash into each other. None of those situations are very specific and unique to solving the problem. In other words, momentum is conserved in any collision. It doesn't matter. In fact, you could even have, if you really want to go there, you could even have a situation where 2 is going to the right, but 1 is going to the right faster and catches up and bangs into 2 from behind. Okay, that could be the case too. But let's just simplify this and say that 1 is moving, 2 is not, they smash into each other. Okay, and afterwards, they move, but with separate velocities. Okay, so in this situation, this is a conservation of linear momentum problem. Linear momentum, again, is conserved if there are no external forces acting on the system. And when 1 crashes into 2 and 2 crashes into 1, they apply a force on each other and thus have equal and opposite impulses on each other at the same amount of time, but they don't, there's no external forces acting during the collision. In other words, no friction, there's no applied force, no tension, nothing external to the system. This is also referred to as an elastic collision. Okay, so when you see the phrase head on and they don't stick together, that is an elastic collision. Now, what would we need to know for an elastic collision? Well, we need to know two things. One, we need to know that the momentum initially before the collision is equal to the momentum finally after collision. I'm just going to rewrite this as momentum before is just P and momentum after is P prime. So instead of writing initial and final, I'm going to write final with a little prime notation subscript. Okay, now what does this translate to? It translates into, and this is where you would need to look and see what has momentum before and after collision. So mass mass and velocity of object 1 plus the mass and velocity of object 2 equals the mass times velocity of object 1 after collision and the mass and velocity of object 2 after collision. Now, since this is also an elastic collision, that means kinetic energy is also conserved in the collision. So kinetic energy before the collision equals kinetic energy after the collision. That's a pretty fundamental concept right there. Okay, in the next scenario, we have two masses that are going to run into each other head on, but this time they're going to stick together. So we're going to take our similar sketch from above. We're just going to steal this sketch right here. And we're just going to do something to it. Instead of having mass 1 and mass 2 move off at different speeds, they're going to stick together and move off at one speed together. This is also a conservation of momentum problem, but this is referred to as an inelastic collision. Now, an elastic collision is one in which the kinetic energy is the same before and after. In inelastic collision, there's always going to be a loss in kinetic energy during the collision. Some of that kinetic energy is transformed into other things. Internal energy of the molecules that make up the object, the surrounding air molecules, some heat is transferred to the surrounding air molecules, sound energy. That energy basically becomes something else. So there's a loss in mechanical energy associated with this. Now the equations that we're dealing with, very similar. In fact, I'm going to go ahead and copy these two straight from the equation above. Momentum before equals momentum after, but here's the key difference. Since the two objects stick together, they don't have a v1 prime and a v2 prime anymore. There is just simply a v prime. And so I'm going to pull this out. I'm going to pull this out. And this becomes the total momentum after collision, which would be the sum of the two masses stuck together times their common velocity, which is not v1 prime or v2 prime anymore. It's just simply v prime. Well, what if the two objects start off at rest and then separate? So anytime we're dealing with two objects that collide or separate, it's going to be a conservation of momentum concept. So we can start with that right off the bat. But the picture, okay, could be viewed in many different ways. It could be two people that are facing each other. And let's say those two people push off each other and they apply a force in opposite directions that make them move in opposite directions. It could also be, for instance, a gun firing. So a gun fires a bullet forward, the gun itself recoils backwards. Same thing with a cannon and a cannonball. Same thing with a rocket taking off. Same thing with an astronaut or a space shuttle moving in space. It has to expel gas. So if gas is expelled one way, the astronaut or space shuttle move the opposite way. So what we have here is we have a case of separation. Separating masses also conserve momentum. Now, We're going to start with the same idea, okay? But here's how we're going to differentiate this equation. Initially speaking, both objects will not have momentum. So no momentum to start with equals momentum to end with. So how do you get two objects to add up to no momentum? Well, we simply move one of these to the other side, and you get equal and opposite final momenta. Now, what if we have two masses that run into each other, but at different angles? So let's say we have a mass that's moving and it runs into another mass, and then sometime later that first mass moves off at this angle and the other mass moves down at that angle relative to the horizontal. Well, this is also a conservation of momentum problem, but these are referred to as glancing collisions. Okay, and how do we approach a glancing collision scenario? We take the same equation, but we write down the formula for conserving momentum twice. Once for the x direction, and once for the y direction. What if we have a scenario where we have a force versus distance graph for a stretch spring? Now there's two things that can result from this. Okay, there's two different concepts that can result. The spring constant is something you can get from this. And the work done by the spring, otherwise equal to the amount of spring potential energy that is stored in the spring. The slope is going to equal K, the spring constant. The area is going to be the work under the force distance graph. Now, what if we have a mass that's being forced over a particular distance? Well, a mass that's being forced over a particular distance, that's a work concept right there. And the formula that goes with that is a parallel force times distance. Now, what if we're given more information? What if we're given a force that's causing something to speed up or slow down over that distance? We're starting to give more variables involved. Well, we still have the same thing, but maybe we're speeding up or slowing down. Well, if we're speeding up or slowing down, that's a Newton's second law scenario, but it's also a work energy theorem problem. These two ideas were linked. Okay, and they're linked in the following way. Newton's second law, net force equals ma. You guys again need to know that net forces can be written as causing forces minus opposing forces equal ma. And then you simply look at the actual force diagram to see what those causing and opposing forces are. Now, the work energy theorem states that the work is equal to some sort of change in energy. Now, usually that change in energy is going to be a change in kinetic energy, more often than not. So we could actually rewrite this as the work, which is force times distance equals 1/2 mv squared minus 1/2 mv naught squared. Or you could write initial and final, if that works too. What if we have a mass that's slowing down on its own as it moves over a rough surface? Well, if it's moving over a rough surface, friction is the thing that's causing it to slow down. So it's moving this way, okay, with velocity, but it encounters a rough patch over some distance d. That right there would be specifically the work due to friction. And it's the same formula that we encountered before. Okay, work due to friction. We're still going to have Newton's second law at work here. But specifically, you have no causing forces. And the only thing you have is friction. So friction, negative friction, equals ma. That's why it's slowing down, right? It's an opposing force. But you also have work energy theorem at work at this scenario too. And specifically, the force would be a friction force. And since it's an opposing forces do negative work, so it's negative force times distance. And there is no final kinetic energy because it comes to rest, so negative force times distance equals a negative 1/2 mv squared, or force times distance equals 1/2 mv squared, where that force is friction. And yes, you could turn that into mu times normal force in a substitution as well. And then lastly, what if we look at the time it takes for work to get done? Well, in that instance, we're looking at an object that's being forced over a particular distance, but it's also being forced, and you're clocking the time that it takes for that force to apply itself over a distance. That is referred to as mechanical power. Power is the rate at which work is done. And it's the change in energy over time. Usually it's written as work over time. Or, if you remember that work is force times distance over time, then distance over time is speed. So force times the velocity would be another way to write it. All right, let's take a look at the next scenario. In this one, we have a situation where a mass could, but does not rotate due to the forces that are acting on it. Let's take a look at what that might look like. One possible example we could draw is simply a beam supported at some fulcrum point. And at that point, we could have a couple forces acting on it in different directions. This force on the right-hand side causes a clockwise torque. Whoopsie. And you can see that this force over here causes a counterclockwise torque. And so what we have is a situation where we have equal and opposite torques. And so we can write up the concept as what is called rotational equilibrium. Which is another way of saying balanced torques. Now, we're going to need a couple of equations to reference this. One, we're going to need the actual equation for torque, which is a perpendicular component of force times the distance of a lever arm. The distance of the lever arm is defined from wherever the force is applied to that point of rotation. The other thing we're going to need is to balance our torques. That means any torque that is clockwise, all the torques that are clockwise balance all the torques that are counterclockwise. So CW is clockwise, CCW is counterclockwise. Let's say we have another situation where we have a mass that's rotating, but we're specifically given units like radians per second, revolutions per minute, or the fact that it's spinning faster or slower. Well, we have our mass. Let's say it's just a ball or a sphere or something, spinning on an axis with omega angular velocity spin. Let's say it's counterclockwise. And let's say that we're only given omega and alpha. So if you're only given omega and alpha, you're given rotational kinematic variables. So this would be a rotational kinematics problem. Now, rotational kinematics can be broken down into two areas. Could either be rotational constant velocity, or it could be rotational constant acceleration. It's going to be one of the two. Okay, now if it is rotational constant velocity, there is one equation that goes with that, and that is simply that you can write it two ways. You can write it theta equals omega t, or we can write it as omega equals delta theta over t. It honestly doesn't matter how you write it. It's the same equation. If it is a constant acceleration in a rotational frame of reference, then we have three equations. Omega equals omega naught plus alpha t. Theta equals omega naught t plus 1/2 alpha t squared. And omega squared equals omega naught squared plus 2 alpha theta. Okay, so that would be a rotational kinematics concept. Now, what if we have a situation where we're given, again, a rotating mass, but this time the rotating mass is spinning faster or slower specifically because of forces acting on them, meaning torques cause the rotation. So let's say we have a wheel that's spinning, okay? And let's say it's spinning like this right here, where we have counterclockwise omega, and we're spinning through that axis. And maybe it's spinning like this, where there's a force applied relative to that radius, which would be the lever arm. So you can see this force would cause a torque. And if it's spinning faster, that means omega spins the same way that alpha does. So the angular acceleration would spin the same way as the angular velocity, both counterclockwise. If, for instance, this force were applied on the other side of the wheel to slow it down, so the wheel's spinning counterclockwise, but the force is opposite that, well then of course you would have angular acceleration opposite the angular velocity, and indeed we'd have a situation where the wheel would start to slow down. So that's why I put or. Could be either of those situations. Well, let's go ahead and move that back over here, and let's just work off of a scenario where we're speeding up due to a force applied on a spinning object. That would be a net torque problem. And specifically, net torque, there's the main equation for that is net torque equals I alpha. It's analogous to net force equals mass times acceleration, but these are in terms of rotational variables. Now, of course, in order to do this, you're also going to need the torque equation, which is a perpendicular force times distance, but you're also going to need to substitute for alpha. And recall that alpha is equal to, or A, the tangential acceleration is equal to R alpha, which means alpha is equal to A over R. You will need to make that substitution right here. And you will have to substitute for I, which is the rotational inertia, but those formulas are always given to you. Depends on the geometry of the object. It could be a disk, a solid sphere, it could be a point mass revolving around something else. But you'll always be given that. You do not need to memorize the rotational inertia. Well, now let's say we have a mass that is curving because of forces acting on it. So let's say, for instance, we have a mass that would be very comfortable going this way, but instead a force is acting on it this way, perpendicular to its motion, and then the force ends up here, or the object ends up here, with still that same force acting on it, but now the velocity is headed in this direction and causes it to rotate more, and the force is still here. And so we have a situation where we have a center pointing force that causes curvature. And a center pointing force would be a centripetal force. Centripetal forces are just an application of Newton's second law of motion. So specifically, Newton's second law is net force equals ma. But this is net centripetal force equals mass times centripetal acceleration. So you do need a formula for centripetal acceleration. A is equal to v squared over r. So putting it together, net force equals mv squared over r. But don't forget, you do have to be able to work that into the individual forces. So that could be written as causing force minus opposing force equals mv squared over r. Now, when we're talking about forces that cause curvature, causing forces point into a circle. Opposing forces point out of a circle. So forces in minus forces out equal mv squared over r. Well, let's say we're given a situation where we have two masses separated by a distance. Well, two masses, let's say this is m1, let's say this is m2, and they seem to be separated by some distance r. That is a situation known as universal gravitation. Newton's law of universal gravitation. Universal gravitation for short. Now, there's one formula that goes with that, and it's F. You can write F sub g as gravitational force equals big G times m1 times m2 divided by r squared. Now, let's say we wanted to find the acceleration on another planet, like on the moon or some other planet or a comet or you name it. We want to find the acceleration due to gravity somewhere else. Well, what we need is this. We need to be given the mass and the radius of that moon or planet or whatever it is. Okay, so you're given a mass and a radius, and you're good to go with this concept here. And it's basically the acceleration due to gravity, but on another planet. So it's acceleration due to gravity, which is g on a planet. So you can really just shorten the concept to g on another planet. Finding g on another planet. Well, finding g, the acceleration to gravity on another planet, it basically uses the same idea, because you got to remember the gravitational force, that's also the weight. So if gravitational force equals mg, and we set those equal to each other because clearly both of them are equal to fg, then we get the following. I'm going to derive it for you first, and then I'll write the equation. So mg equals g m big M over r squared, where this is the mass of what is being orbited, the satellite, whatever that is, and this is the mass of the planet. You can clearly see the mass of the satellite cancels, and we're left with little g, the acceleration due to gravity, is equal to big G, the gravity constant, times the mass of the planet, divided by the radius squared. Very similar to this equation, and it was actually derived using that equation. Okay, now let's say in the next example we have a mass that is revolving around something. Say it's a mass revolving around something else that's you're given, a mass and radius. in this. So let's say it's going like that. Well, there's several concepts that could relate to this. One, how do you go in a circle unless a centripetal force keeps you in a circle? So it makes sense that centripetal force might be a concept in this. Gravity would be that centripetal force pointing to the middle of the circle. But if it's a centripetal force problem, it's also a uniform circular motion problem, right? Since it is centripetal force involving gravity, it could be a universal gravitation problem, right? And since it involves a point mass revolving around something else, it could even involve rotational inertia of that object. So in fact, there's even more concepts than I've listed here. These are just 4 that come to mind right away. Now, if these are the 4 concepts you're going to use in this question, then net centripetal force equals mv squared over r. If we're talking about uniform circular motion, then v is equal to 2 pi r over t, where 2 pi r is the circumference of the circle divided by the period of the time around. We also need the universal gravitation law, which is g m1 m2 over r squared. And then, the rotational inertia of a point mass, right, is I equals mr squared. So a lot of concepts and a lot of formulas could be used for something as simple as something revolving around something else. Now, what if we have a position versus time graph for a mass moving horizontally or vertically? And again, they could look a variety of ways. Position time graphs could look like this, they could look like this, they could look like this, they could look like that. They could look a lot of different ways. So I'm just going to draw any generic position time graph. So if we're given that, this is definitely a motion graph type concept. And what do we need to know about this? Specifically, you need to know one thing really, and that is the slope of this graph at any one point in time is the instantaneous velocity. Now, if it happens to be a straight, so if it happens to be a curve, the slope at any one moment in time is the instantaneous velocity. Now, what if it's a straight line? Then the slope of that line equals the constant velocity, the average velocity, but the average of a constant value is that value. So it would equal the constant velocity. All right, in the next scenario, let's say we're given a velocity time graph. Just any velocity time graph, well, doesn't matter. It's also a motion graph concept. But here's what we need to know about a velocity time graph. There's 2 things we need to know about it. Number 1, the slope of the graph equals the acceleration, the constant acceleration that the object is undergoing. The area under is the displacement, how far the object has gone. Now, what if we're looking for an acceleration time graph? Now, acceleration time graphs are only going to look one of 3 ways. So only one of 3 possibilities. It's either going to be constant horizontal, positive horizontal, constant negative, or 0. It's got to be one of those. Okay, also a motion graph type of problem. But now specifically, there's nothing we can do about slope in this level of class. The slope of this does equal something, but it's not a quantity that we study. For us, the only thing we're going to get out of an acceleration time graph is the area, and the area would help you figure out the velocity. Now, for this last scenario, what if you're given a force versus distance graph for a moving mass? Just some random force distance graph, kind of like that. Well, if we're dealing with a force distance graph specifically, that is a work concept. And work can be found by finding the area under a force distance graph. Okay, ladies and gentlemen, I hope you found this helpful. Again, please rewind and pause as necessary. We'll see you next time. The following concepts are add-on or additional concepts that differentiate the AP Physics C course from the AP Physics 1 course. Let's take a look at what some of these concepts would be and how we recognize them. Let's take a look at the scenario where we might be given a planet with an orbital radius or orbital period, orbital period. So we're given orbital period and orbital radius. This would be a Kepler's third law concept. Which we can abbreviate as K3L. Now, Kepler's third law, I'm going to derive it for you first, and then I'm going to show you what it is that you need to be able to know and write down from an actual equation point of view and a proportion. So it works this way. Kepler's third law was derived using the idea that gravitational force is a centripetal force. So gravitational force, G m1 m2 over r squared equals mv squared over r. And if we're talking about a satellite and the bigger mass that it's orbiting, let's change it up. This is the mass of the satellite, mass of the satellite, mass of the object being orbited. You can see a few things cancel. And so we're left with Gm over r equals v squared. Now, you might recall that v for uniform circular motion is equal to 2 pi r over the period t. Now, even though Kepler's first law states that planetary orbits are elliptical, they're close enough to being circular to apply uniform circular motion principles. And so if v equals 2 pi r over t, and we have to substitute for v squared, then v squared would be equal to 4 pi squared r squared over t squared. And so we'll substitute this for v squared. And then lastly, if we substitute and we kind of solve this equation here, I'm going to multiply both sides by r. And when I do that, it gets rid of the r, and it makes this r cubed. Now if I take this and I swap it out with this, we get Kepler's third law. So Kepler's third law can be written as t squared is equal to 4 pi squared r cubed over g m, where m is the mass of the planet that's being orbited. Now, you could write this as a proportion that really states the square of the period is proportional to the cube of the radius, where 4 pi squared g and mass of the planet being orbited are all constant values. What if we're given force as a function of time? We're given some f of t. Well, if we're given force related to time, that is an impulse problem, but it's an impulse problem given the fact that you have a force time function. So it's an impulse integral. where J normally equals F times delta t, force times delta t. But the force is a variable function. So this time we would write it as J equals the integral from t initial to t final of F sub t dt. What if we're given force as a function of displacement? Well, in these instances, that's going to be a variable work problem, just like this is a variable impulse problem. And in much the same way, work is equal to force times distance, or you could write it as force delta x. Well, if we're talking about this, the work, which is equal to a change in potential energy, is equal to the integral of the force function, force is a function of x, dx. So this is my variable force function, and this is my differential with respect to x. From x initial to x final. And if we're given velocity as a function of time, well, this is a kinematics problem, but it's a variable kinematics. So if I'm given velocity as a function of time, then now variable kinematics work off of the idea that you have to use either differential or integral calculus. So two things occur when we're given a velocity as a function of time. One, in order to find the displacement, I have to take the integral of the velocity function with respect to t. If I want to find the acceleration, then I'm going to find the slope or the derivative of the velocity function with respect to t. If I'm given position as a function of time, similar idea. It's also a variable kinematics problem, meaning kinematics with polynomial-based calculus. And in this case, the only thing I can really do with a position function is find the velocity, and the velocity is the derivative of the position function with respect to time. Now, what if I'm given some resistive force as a function of velocity? Well, here I'm given some resistive force as a function of velocity. It might be given as F equals kV, or I've seen it written as F equals BV. There might even be a negative put in there to indicate that it's resistive. But basically, you're given some sort of resistive force as a function of velocity. This is a resistive force problem, but all resistive force problems are themselves Newton's second law problems. Okay, so we're still going to use net force equals ma. We're still going to use causing force minus opposing force equals ma. But here's where resistive force, if you recall, becomes a little different. And that's why I'm going to derive it in blue. Causing force minus opposing force equals m, and you need to replace a with the derivative of velocity with respect to time, meaning write it as a differential equation. In the next scenario, we're given energy as a function of time. So how does energy relate to time? Well, if I'm given some sort of energy as a function of time, then that's an instantaneous power type of concept. And power relates to the rate at which work is done. So if I'm given position as a function, energy as a function of time, power would be taking that energy function and taking the derivative of it with respect to time. So taking the derivative of that function with respect to time would give us the instantaneous power. All right, now what if we're given a mass that's rotating through some other place other than the center of mass? So for instance, if we had a rod that was rotating through the center, well, then that's rotating through the center of mass. But what if we weren't rotating through the center? What if we were rotating about the endpoint? Well, then all of a sudden, you're rotating through an axis that is something other than the center of mass. There's the center of mass, there's the point of rotation, and let's say the whole thing is rotating about that point other than the center of mass. It could be rotating here or wherever, but some other place other than the center of mass. This is a parallel axis theorem concept. And the parallel axis theorem equation helps us find the new rotational inertia through that point. And it's taking the rotational inertia through the center of mass, and we're going to add to that md squared, where m is, of course, the mass, and d would be the distance from the new axis to wherever the center of mass is. And finally, what if we're given potential energy as a function of displacement? So we're given a u of x function. Well, this is this would be a variable energy and force problem, and the equation that results from that is the force is equal to the negative derivative of the potential energy function with respect to position. I hope that helps. Again, please feel free to pause and rewind the video as needed. Thank you.